Okay, good morning to everyone. So, this is about how to find out the effective length of a column. Now, what we discussed so far is that I have got a column with boundary conditions of both and hinge, right, both and hinge. Then I have boundary condition of let us say one end fixed, second is free, third conditions what I had the fixed and other end also fixed. The fourth condition is the fixed and other end is your hinge. For all the conditions, what will be my PCR, right. So, now if you look at carefully, so what we learn here is this is the pi square E I by L square, right. So, this is what we learned, pi square E I by L square, or rather I will write a small l. L square. Now, if it is
Sir, free not showing, sir.
I am very sorry. Okay. So, now this is what I am trying to write down is a critical load PCR, critical load capacity, right, capacity of column with a different end conditions, right, or we can say boundary conditions. So, also called end conditions, right. So, now we said the first condition was both end hinge. So, pi square E I by L square was the load carrying capacity, right, that is your PCR. Now, if it is fixed and free, what we learned that the load carrying capacity was pi square E I by 4 L square, right. Then in the next fixed what we saw that is pi square E I, it is 4 times pi square E I by L small l square. Then for the purpose of the fixed and hinge, 2 pi square E I by L square, right. And we also said this is an ideal column, right, ideal column. This is an ideal column, and we compare all other column end conditions according to the first one, right. This is what we learnt. Now, if you carefully see, if you carefully observe, right, if you carefully observe the end conditions at the length what we are getting here, right. So, we say what is the effective length if you want to know, right. So, if you carefully see, let us say effective length is my, let us say L, right. So, effective length, if I say L is my effective length, right. So, for ideal column this L becomes L, L is L. Now, if I compare second case, right, second case which is one end fixed, other end free. So, pi square E I by 4 L square is compared to pi square E I by capital L square. So, what I am going to get? Cancel, right. So, what are you going to get? Capital L square is equal to 4 small l square. So, capital L equal to 2 times L, 2 times L. So, the effective length L effective, let us say L effective will be your twice of the length, right. Now, similarly, when you try to go for the third condition which is fixed, so what I get? 4 pi square E I by L square is equal to pi square EI by capital L square. Always I am comparing with the ideal column. So, what happens? Pi square EI by L square, pi square EI cancel. So, what I going to get L square is equal to L square by 4. That means L is equal to L by 2. So, this L effective will be equal to, let us say double F, equal to L by 2. And if you look at the third case, what I am going to see? That is a 2 pi square E I by small l square equal to pi square E I by capital L square. So, pi square E I, pi square I get cancelled. So, what you left with is capital L square will be equal to small l square by 2. That means, capital L equal to your L by root 2. So, this L, capital L means L effective will be equal to small l by root 2. Right? This is your L effective. So, effective length is this. So, if you carefully, what I am going to do now, if you carefully try to see in a diagrammatically what this effective length means, I will show you a pictorial form to see what is this diagrammatically mean. So, what I do that I will draw a line. Suppose this is your dotted line ankondi, but it does not matter, I cannot make it. I have another line, right. Now, I will try to draw a column. This is, let us say, this is a column, straight column having hinge here and hinge here, right. This is my ideal column. So, now if I try to draw the buckling shape of this, something like this, right. So, this is the buckling shape of my column. So, this will be my buckling shape of my column. Now, I am assuming that this length is my L, this length my L, column length, right. This is my column length. Now, if I take the, let us say, second case which is fixed, what is our second case? Fixed free, right. Second case is our fixed free. So, now my second column will be this is a fixed, right. So, I have fixed here and it is free here, right. A free here, free means not hinge, please do not misunderstand here. So, it is free here. So, what I did, when I apply a load, it is going to buckle, when I apply a load it is going to buckle something like this. No, okay, something like this, right. So, this is my buckling behavior, right. This is a P, whatever I am applying load here also something P, let us make. Okay. Now, I am talking about second case. Now, if extend this line, it goes something like this. The same curve will continue like this till, now if I try to draw this from one end of the free to the next end, this will be my 2L. This is what meaning by my effective length for the fixed. One end is fixed, other end free. So, the effective length becomes twice. Right? It means too slender, that meaning the column is having too slender. It is very risky, that kind of columns. Okay. So, anyway, you understand, this is mean effective length. Now, let us go to the third case. What is the case? Which is fixed fix. So, if I try to draw a fixed column which is fixed here and a fix here, right. So, now if I look at the behavior of your buckling here, what happens is something like this. This is buckling behavior. It does not start immediately buckling here, it is after some distance buckling starts. So, what is this my effect length here? What I told you, the effect length is your third one, it is your L by 2. That is nothing but this. This will be my L by 2. Only L by 2 portion of my column buckles. In the first case, full column buckles. The buckling is there from the beginning to the end. Here, buckling is there from beginning to the twice length. It is buckling is there, right? That is very difficult to imagine the second case, right? Now, let us go to the third case. If I look at the third case, so what I have is your one end fixed, other end is your this is a column, it is fixed at one end and hinge at other end, right. Now, if you look at the buckling behavior of this column, because whenever there is hinge, the buckling start from there, and whenever they fix, buckling ends somewhere in early only, something like this. Okay. So, practically buckling started somewhere here up to the end here. So, this length we call it as L by root 2. This is nothing but 0.7 times L. This is your 0.5 times L. This is twice L is L. This is what it means, the effective length. It is pictorial form. This is your equation form. That means, in effective, that effective length means the how much length of the column will have a buckled up, right. That is the meaning. So, what this indicates that you must use, if more the buckling, more the problem, right. More the buckle length, more the problem. This is what you should understand. More the buckle length, more the problem, right. More the problem in the sense means what? Lesser load carrying capacity, load carrying capacity. So, I must see that column have lesser effective length, right. So, it means now which one you will prefer based on this condition. I am going to prefer this, right. First this I am going to prefer, next I will prefer this, and this is the third and this is the last. Whenever somebody asks me to design a column or design a tank or design a building, I will prefer this is the first choice, fix, so that my carrying capacity is very high. I will be a good designer, right. If it is not possible to have arrange both and fix, it is not possible. Generally our buildings we say bottom fix, our columns are bottom fix in the foundation, but foundation, unless you go for a pile foundation, bottom cannot be assumed to be fixed. That means bottom is hinge, So, I can, of course, this I can assume to be bottom also, does not matter anything. So, bottom hinge is fixed, bottom is hinge. So, top one, because the building will have laterally sway. So, generally this is the case, most generally practically this is what happens, unless you purposely make some columns to be make a piling and make a fix, this is not, this is going to be ideal case. Ideal case is going to be always designer prefer this, you are going to use it, prefer is this anyway, but not possible practically, he will use this. Okay. Having said this, so what I am going to do, what is the Euler's formula, the Euler theory, the assumptions made to derive the equation. Okay. So, what I want to do now, the assumptions made, discussion on assumptions made, very important, made in Euler's theory, because any theory has some fundamental assumptions beyond which that theorem does not work. You must understand that, and you may get a questions in examination. So, the first important point is that the column is initially perfectly straight before the load are applied. That means, if I take a column, this is a column, okay. So, this is a column, but if generally if I bring a column somewhere, something like this, right. See, the way I am ready to draw, I am not able to draw straight. That means, it is practically, that is how people can make a straight, but when it comes to side, it will be slight tilting. See here, little tilting is there. That may be because of so many practical situations. If you take a steel columns, it is people bring in tailors and throw from tailors on the ground. So, because of which there will be little bent, then this theory will not work for this kind of columns. So, very ideal, right. So, it means column must be straight, straight column before loading. Right, this very important, perfect straight. Okay. The second important assumption we are making is the section is uniform throughout the length. Section is uniform. That means, you cannot use a column something like this. If this is a column, I am going to put a load like this, our theory will not work for this. Section is uniform throughout the length, right. So, this theory works only for the uniform length of the column. Okay. The third important assumption is column material is perfectly elastic, homogeneous, isotropic, and obeys Hooke's law. Right. The material of the column, right. What is that? Elastic. Elastic means must obeys the Hooke's law, right. Apart from this Hooke's law, you should also have a homogeneous, isotropic, very important assumptions. Do not think it is simply I can read and so that means in Hooke's law valid, that means I told you that your stress at yield stress is always more than your sigma CR, means your buckling is going to be earlier than your yield, is it not? That is what I told you in the beginning. Only then this value, if it is not going to be going to yield first, then this particular theory, Euler theory will not work, right. Then definitely another thing is, even if it is elastic, the material is not homogeneous and isotropic. That means, your material property is not same in all directions, right, and in different planes. So, then this particular material will not, Euler theory will not be valid. So, next is the length of column is very large compared to the lateral dimension, right. That means, the length of the column is very large. That means, suppose I have a column to be, let us say 4 millimeter, this is your 10 millimeter, let us say, the length of column should be 1 meter, right, something like that. So, long enough, so that when I put a load, it has to buckle, that is my idea, right. But suppose I have a column something like this, very thick, 1 meter by 1 meter thick column, 1 meter by 1 meter thick cross section, and a length is only 1 meter height, 1 meter height. Try to understand, 1 meter by 1 meter, or I mean huge cube, it is not going to buckle, it is going to only yield at all, if at all you are applying more load. So, in such case, this Euler's theory will not work. I told you, right, you can very well imagine that stress diagram. This is what, how it is going to be, lambda. So, at particular lambda, if suppose you take a steel or column, I mean concrete, so this is your sigma CR. So, at beyond this value of lambda, certain value of lambda, let us say 89 for steel. So, this is not going to work. What is mean by this? Lambda lesser than this means what? It is going to be a short column. Short column means a shorter length of the column with higher dimension cross section. So, you are the column section going to be beyond this is going to be yield, not the buckle. Anything lesser than this is going to buckle, anything more than this is going to yield. So, your Euler theory is valid only within the range, lambda more than this, that is meaning. So, I will write here, this is for the column, length of the column is more than the lateral dimension. Let us say lateral dimension, least lateral dimension, dimension is much smaller, much smaller, something like this you have to write, much smaller, not equal to, much smaller to your length of the column. Okay, very important. Each of the assumptions is going to be very important, maybe from the gate point of view you have to remember this. Now, the next assumption is the self weight of the column is ignorable. Self weight of the column, when I am trying to apply a load, I am not worried about the self weight of the column. That means, self weight of the column is not going to be any way any way problematic to my buckling. Self weight of column is to be ignored, right. So, this is not going to be a part of my contribution to the buckling. So, the next important is that the direct stress is very small compared to the bending stress corresponding to the buckling condition. That means, the direct stress means what? Sigma y, that means P by A. This is going to be very small compared to the bending stress corresponding to buckling. Bending stress means it is buckling stress only. That means, when you apply a load P, so it is going to buckle rather than crush, that is meaning. So, this is going to be very small compared to the sigma CR, that is what I already told here, right, somewhere here in the top I mentioned, here only I mentioned, right. Sigma CR is going to be very less, right. So, the yielding will be much later, the direct stress, that means P by A is going to be very less direct stress, not, it may not yield here, it may not yield here, but the direct stress is your P by A is going to be very less, very small compared to the buckling. So, it means buckling going to occur first, okay, buckling occur first, okay. That is very important assumption in your important assumption in case of your Euler theorem. So, very important is the column will fail by buckling alone, not bending. Right? Sometimes the column will fail also in bending. For example, the column fails only by buckling. That means what? Suppose I have a column something like this. This is my column, right? Let us say I just kept it here. So, this is a CG. I instead of applying load from here, I apply, let us say, load from here. So, what happened? There is an eccentricity, right? Because of eccentricity, that means I am applying a load on the column equal to P and with a moment of P into E. So, that means I am applying a moment also. So, this Euler theorem will not work for this kind of columns. That means there should not be any movement on the column, pure axial load only should be there. See the kind of the so many if and buts, right. Now, next the loads are applied at the ends of the column and without eccentricity, that is what meaning again. This is also same thing, maybe buckling without bending, maybe bending. I can also have a lateral load here apart from axial 4, right. So, this also not should be there, and eccentric loading, concentric loading should be there. That meaning concentric load only should be applied to be only concentric load to be applied, and the columns and its supports have no imperfections. That means column ends or in the section or in the sections, imperfections should not be there. What is mean by imperfections? Imperfections should not be there. For example, suppose I have a column something like this and I put embedded in the concrete this steel column and applying a load here, but in the concreting lot of honeycombing here, honeycombing means this concrete not proper. So, after applying some load, what happens? This get settled inside, right. So, it will be something like this. So, what we thought a fixity, it is no more fixity, it becomes hinge because of the end imperfection. Imperfection means faults, or column like kind of fault undanukondi. Suppose there is a hole here, somewhere hole here, you made a lot of holes here somewhere, maybe because of for bolting purpose or some purpose you made a hole. So, what happens? That is the portion where the buckling starts, like that is weaker section, buckling starts. So, column should not be like that, okay, very important. Then the last important assumption is that the end pins are so made that column is free to buckle about any axis of the cross section. The end pins, right, end pins or whatever fixtures, whatever you made it. So, those sections should be so perfectly made so that free to go any direction it wants. That means I can just like a column here, this is a column here. Now, I have a plate like this, on the top of which I make something like this, a groove, and make a nice ball here, and also at top I will make another groove like this, and I fix this on the top. There is a girder here and load is coming onto this, and similarly bottom also I make kind of a roller here. Roller is rested in other direction. So, perfectly spear. So, these are a spear. So, if I put a spear top, spear bottom, then whatever my load applied is perfectly concentric, and also the column is free to buckle either this direction or this direction, right. Any direction it can buckle. So, if I take a rectangle column, so it may buckle this direction or this may buckle this direction, any direction. So, you should not restrain it, right. Otherwise, if you restrain something, this particular Euler theorem will not work. right. So, that means perfectly you should have a spheres at the top of the column, right. Who can provide like that? Can you see anybody in the real time going to provide perfect balls? No, right. We cannot even provide perfect fixes also, right. So, these are all ideal situations where the Euler theorem works. So, the Euler is ideal candidate, but in the reality, in a real life, ideals will not work, ideal things will not work. I already gave you. So, pin ends are not possible for all the time. I can just give you the comment on each of that, and go back to the starting from first one. I gave you straight columns, practically not possible straight columns, because it is, even if you manufacture here also, I mean only you can manufacture columns, concrete column also very difficult, right. So, this, right, the steel columns coming from steel plant or somewhere factories, definitely transportation has a problem, right. So, this is not possible practically most of the times. Section is uniform in the section, may not be, somewhere some small bend will be there, dent will be there. Concrete, definitely there will be a problem, right. Then material column is perfect elastic, fine, that may be somewhat true. For steel columns it is true, for concrete it is not true, because your laborers are making the concrete. So, definitely they do not make proper, some in between we will have some papers, polythene covers, any dust is part of your concrete when labor makes the concrete, right. So, and they do not vibrate properly, lot of air pockets left there. So, that means not homogeneous and definitely not the isotropic, but any steel columns may be somewhat these will obey, but sometimes there may be some defect inside also there also, but it is more or less we can say perfect in the material in comes to steel. Now, again the least lateral dimension should be much less than length, fine, that is a part of a designer has to choose that is okay, this you can follow. The fifth one, self-added columns to be ignored, fine, I can ignore it, but sometimes if you take a huge column, so definitely weight is very heavy. If you take a concrete column, weight is much more than your live load. And sixth is your FCR, means a critical stress must occur before the normal stress is fine, that may occur. Column fails only by buckling. Practically most of the times column will buckle because of the lateral load, because of eccentricity, because some wind comes, followed by your already axial force is there, wind load comes, then it is going to first bend then buckles. Because of lateral load, it's first they are going to bend like that. We have a column like this, because the lateral load is going to bend. Now, it becomes a fixed free, then it is going to buckle then, right. Then concentric load to be applied is practically nobody is going to do that, it is not feasible at the site, practical concentric load, and column bends to be perfectly, which is not possible practically, right. So, end pin to be end perfectly without any mistakes is not possible. So, it means the Euler is like myself, a parent looking for his children to become perfectly ideal. My son will take only 20 rupees from a pocket money, goes to school college, spends 10 rupees for the bus and reaches there, goes by walk from Komadi to college and return, go by walk up to Komadi, take a bus, comes home. That is all. He will not go do anything else, he will not move around, he will not do any mischief, studies neatly, sits in the first bench of the classroom and takes notes nicely, he will not throw their bags, he will not lose his pen. So many ideal conditions a parent like me will expect from the child, okay. But all 10, more than 10 assumptions a parent makes for a child, but practically it is not the case. You know, all of you are practical example of that, it is not possible, right. So finally, I will just explain what is the limitation of Euler. Of course, there are a lot of limitations, these are ideal conditions he is assuming. So, what is the limitation, very important limitation of this Euler theorem? Very important limitation, fundamental limitation. I mean, other things are not possible, but the limitation of this theorem is that somebody may do all this perfectly, fine, but there is important limitation is that what you saw if you look at carefully the pi square, the PCR, we said pi square E I by L square, then pi square E by I means A into R square, R is radius of gyration by L square. This also means pi square E by L by R whole square, and the A goes other side, that is a PCR by A, right. Then I say PCR by A is your sigma CR is equal to pi square E by lambda square, that is slenderness ratio. Now, if you carefully see, that means for this particular stress should be true for any lambda, because he here did not say anything. Pi square is pi, E is E, lambda is lambda, lambda is L by R. That means for any L, for any R, this formula should work, stress should work, is it not? But if you look at carefully, for E equal to 2 into 10 power of 5 Newton per millimeter square, right, with this, and then if try to write down this and try to get maybe sigma CR, maybe yield stress of sigma y to be your 250 MPa Newton per millimeter square, which is the one of the yield stress of a steel material. Then what I am going to get lambda, already I told you lambda is going to be something around 89, slenderness ratio is 89. That means what, only up to the lambda equal to 89, any more than this critical lambda, right. So, any lambda more than 89, only this value is going to be buckling, right. That means the column going to buckle only when lambda more than 89, but lambda less than 89, it is not going to be, for lambda more less than 89 not buckling, but it is going to be yielding, right. So, it is going to be yielding. So, the yield stress, the failure of the column taking place by yielding, right. That means any value for a steel of 250 MPa of Young's modulus of 2 and 10 power 5 Newton per millimeter square, the lambda less than 89, this particular column, this particular theorem will not work, yet for lambda less than 89. So, similarly you can work out lambda for, let us say aluminum, lambda for brass, lambda for concrete, you can work out, right. We know your concrete yield stress sigma y is, let us say your 40 MPa, M40 grade of concrete MPa, and your Young's modulus is, let us say 36 GPa, let us say 35 GPa. Based on this you can work out the lambda. I want all of you to work out what is the critical lambda with which I can work out to say that this particular Euler theorem works. Okay. Substitute this E and lambda y Fy, for which your Euler theorem works. So, find out what is the slenderness lambda corresponding to the concrete, corresponding to the aluminum, and maybe another 2-3 material you can see, right. So, this is what limitations of your Euler theorem and assumptions of the Euler theorem. Thank you. Any doubt?